Senior High School Pre-Calculus Core Subject. Circles. Learning goals. At the end of the lesson, the student is able to: Number 1. Define a circle. Number 2. Determine the standard form of equation of a circle. Number 3. Graph a circle in a rectangular coordinate system. And number 4. Solve situational problems involving conic sections on circles. Definition and equation of a circle. A circle is the set of all points on a plane that are equidistant from a fixed point known as the center. The fixed distance to any point is called the radius of the circle. To illustrate, let's say that this point C is the center of the circle. We try to plot several points on this plane and trace as many points as we can to have the pattern of the circle. As mentioned from the definition, the distance from point C to any point on the circle is the radius of the circle. Geometric properties of a circle. A circle is determined by its center C with coordinates hk and its radius r. Radius. The length from the center of the circle to any point on the circle. In the figure, r is equal to the length of the line segment CP. Chord. The distance between any 2 points on the circle. The line segment AB in the figure is a chord. Diameter. The diameter of a circle is the chord that passes through the center of the circle. The line segment MN in the figure is the diameter of the circle. The diameter of a circle is twice the length as the radius of the circle, that is, 2r, or 2 times the length of the line segment CP, which is also equal to the length of the line segment MN. Standard equation of a circle. Where a circle is drawn, it will have a center C with coordinates hk and radius r. A point P with coordinates xy is on the circle if and only if the distance of the line segment CP is equal to r. For such any point then, its coordinates should satisfy the following. This is the distance formula for computing the distance between any 2 points. That is square root of x minus h square plus y minus k square. To compute for the distance r, therefore, we make use of this formula. Taking the square of this expression, we'll have x minus h square plus y minus k square equals r square. This is the standard equation of a circle. If it happens that the center is located at the origin, then the standard equation of a circle becomes x squared plus y squared is equal to r squared, since h and k are both 0. General equation of a circle. The general equation of a circle is of the form ax squared plus ay squared plus cx plus dy plus e equals 0. Given an equation of a circle in standard form, the general equation is determined by completing the squares in both variables. Example: in each item, give the standard and general equation of the circle satisfying the given conditions. Number 1. Center at the origin with radius 4. Let's try to draw first our circle. From the standard form of an equation of a circle, we have square root of x squared plus y squared is equal to the radius, which is equal to 4. Since it is centered at the origin. Squaring this expression, we'll have x squared plus y squared is equal to 16. This is the standard form of an equation for this particular circle. If we try to transpose 16 to the left-hand side of the equation, making it negative, we'll then arrive with x squared plus y squared minus 16 equals 0. This is the general equation for this particular circle. Number 2. Center at -4, 3 and radius square root of 7. Let's try to draw our circle. From the standard form of an equation of a circle, we'll have square root of x minus -4 square plus y minus 3 square equals the radius square root of 7. Squaring this expression, we'll have x minus -4 square plus y minus 3 square equals the square of the radius square root of 7. To simplify, we'll have x plus 4 square plus y minus 3 square equals 7. This is now the standard form of the equation for this particular circle. To get the general form of the equation, we'll perform the square of binomial for both binomials present in the equation, x plus 4 square and y minus 3 square. Squaring this binomial, x plus 4, we'll have x square plus 8x plus 16. For the second binomial, y minus 3 square, we'll have y square minus 6y plus 9. Now, proceed. We'll transpose 7 to the left-hand side of this equation to make it negative. And to simplify further, we'll combine like terms. Since the only terms that we can combine are the numbers 16, 9, and -7, we'll then add these terms, 16 plus 9, that gives us 25. 25 minus 7 is 18. This is the general equation for this particular circle. The next few examples employ a similar manner for computing for the standard and general equations of the circle. With this, the presentation of the solutions for these examples shall go on without explanations. I suggest that you pause the video whenever you need to. Number 6. Center at 5, -6, tangent to the y-axis. Let's try to draw first our circle. This example is a bit different from the previous ones since we do not have a center and radius pair as givens. Take note that tangent to the y-axis means that the circle touches the y-axis only at one point. We can see from the figure that the circle touches the y-axis at point -6, which is 5 units away from the center of the circle. We can therefore see that the radius of the circle is 5 units. We can now proceed with solving the standard and general equation for this particular circle. Number 7. Center at 5, -6, tangent to the x-axis. As before, we need to find the radius of this circle in order to arrive with the standard and general equation. We can see from the figure that since the graph of the circle is tangent to the x-axis, meaning that the graph should be touching the x-axis at exactly one point. We can see that this point is at 5. From the figure also, we can see that the distance of the center of the circle to this point is exactly 6 units. Therefore, our r is equal to 6. We can now proceed with computing for the standard and general equations. Number 8 has a diameter with endpoints A, -1, 4, and B, 4, 2. Let's draw our circle. Recall that in order to get the standard and general equations of the circle, we need the center and its coordinates and the radius of the circle. The center of the circle is halfway between the points A and B. In order to get the coordinates of the center, we determine the midpoints between these points. Making use of the midpoint formulas, we have the x component for C would be -1 plus 4 all over 2. The y component for C would be 4 plus 2 all over 2. Now, -1 plus 4 is 3 all over 2, and 4 plus 2 is 6 divided by 2 would be 3. As for the radius, we can make use of the standard form of the equation of a circle and make use of any 2 points along the line A, C, and B and use their coordinates in the equation. We could use either A and C, or we could use B and C. As for this example, the radius is determined using the line segment AC. Making use of the standard form and substituting the coordinates of A and C in the equation, we'll have square root of 3/2 minus -1 square plus 3 minus 4 square. Simplifying, we have 5/2 square plus -1 square. Squaring the values would be 25 over 4, then plus 1. 25 over 4 plus 1 would give us 29 over 4. Therefore, the radius would be square root of 29 over 4. Since we now have the center and radius pair, we can now proceed with computing for the standard and general equations of this particular circle. Situational problems involving circles. We now consider some situational problems involving circles. Example. Below is a photo of an archway at the National Gallery of Victoria in Melbourne, Australia. The archway is a semicircular arch with radius of 22 feet. Due to the shape of the archway, A person cannot walk through the edges without bumping on the sides of the arch. If given a height clearance of 7 feet on each side from the floor, how wide would be the walk lane through the arch? Let's try to translate the problem geometrically by tracing the shape of the archway into a rectangular coordinate system. A semicircle is half a circle. Given that the radius of this circle is 22 feet, what is being asked in the problem is to determine a point on this circle with the coordinates x and a height 7. Furthermore, we have drawn our circle in such a way that its center is located at the origin. What this means is we can make use of the equation x squared plus y squared is equal to r squared. From here, we substitute the values of y and r. That becomes x squared plus 7 squared equals 22 squared. 7 squared is 49, and 22 squared is 484. Transpose 49 to the right-hand side of this equation, we have 484 minus 49. The difference would be 435. Taking the square root, this would be about 20.85 feet. Now what is being asked in the problem is the width of the walk lane, and what we have computed would be half of that. So what we can do is double this number into 2x and arrive with about 41.7 feet. Let's try another example. A piece of broken plate was dug up in an archaeological site. It was put on top of a grid as shown in the figure below, with the arc of the plate passing through the points A, -70, B, 14, and C, 72. Find its center and the standard equation of the circle describing the boundary of the plate. For the solution, we first determine the center. The center is the intersection of the perpendicular bisector of the line segment AB and the line segment BC. Let's try to define what a perpendicular bisector is. A perpendicular bisector is a line segment which intersects another line perpendicularly and divides it into two equal parts. In a circle, the perpendicular bisector of any chord passes through the center. In the figure, the line segment AB and the line segment BC are the chords of the given circle. The perpendicular bisector of these line segments passes through the center of the circle. Next is we compute for the slopes of each of the line segments AB and BC. Recall that the slope of a line is defined as rise over run. Let's look first at the slope of the line segment AB. The rise would be the measure of distance from the level of the x-axis up to point P. From the figure, that would be 4 units. While the run would be the stretch of distance from the x-coordinate of B, which is 1, up to the location of A, which is at -7. As for the slope of the line segment BC, let's take point C as our point of reference, meaning that the rise would be measured from the level of C, which is 2, minus the height of B, which is 4. As for the run, that would be 7 minus 1. Computing for the slopes, for the line segment AB, we'll have 1/2, while the slope of the line segment BC is equal to -1/3. We then solve for the equation of the line of each perpendicular bisectors and solve for their intersection to determine the center of the circle. Now recall that whenever two non-vertical lines are perpendicular to each other, their slopes will be negative reciprocals of each other. Hence, if a line, say line A, has a slope m sub A, then any line B perpendicular to A, including the perpendicular bisector of A, will have a slope m sub B equal to -1 over m sub A. In the example, the slopes of the chords AB and BC are m sub AB equals 1/2 and m sub BC equals -1/3. Their perpendicular bisectors will therefore have slopes of -2 and 3 respectively. Since we already determined the midpoints of each of the chord, we then have two sets of a point and a slope pair. We can then determine the equation of the line using the point-slope form y minus y sub naught equals m times x minus x sub naught. Let's now determine the equation of the line of each of the perpendicular bisectors. Starting with the perpendicular bisector of the line segment AB. And that would be y minus 2 equals -2 times x plus 3. Take note that -2 here is the negative reciprocal of the slope of the line segment AB, which is 1/2. While y sub naught and x sub naught would be the coordinates of the midpoint M. Simplifying, we'll have y minus 2 equals -2x minus 6. And solving for y, we'll have y equals -2x minus 6 plus 2. Finally, we'll have y equals -2x minus 4. Next would be the perpendicular bisector of the line segment BC. We then have y minus 3 equals 3 times x minus 4, and take note that 3 here is the negative reciprocal of the slope of the line segment BC, which is -1/3. And again, y sub naught and x sub naught would be the coordinates of the midpoint N. Simplifying, we'll have y minus 3 equals 3x minus 12. Then solving for y equals 3x minus 12 plus 3. Finally, we'll have y equals 3x minus 9. To solve for the intersection of the two lines, we use any of the solutions to systems of linear equations: elimination, substitution, simultaneous equations, or Cramer's rule. However, for this example, it would be easier to make use of the simultaneous equations since both equations are expressed in terms of y. What that means is that we can equate both equations to eliminate y, as shown. So what we have is -2x minus 4 equals 3x minus 9. Sorting the terms in such a way that all the x's would be on the left-hand side and all constants would be on the right-hand side, then we'll have -2x minus 3x equals -9 plus 4. Now -2x minus 3x gives us -5x, while -9 plus 4 is -5. Dividing both sides by -5, then we'll have x equal to 1. Next is to solve for y. What we can do is to substitute the value of x to any of the two equations above. Let's say we substitute the value of x into the first equation. What happens is that we have y equals -2 times 1 minus 4. -2 times 1 is -2. Minus 4 gives us -6. We can also substitute the value of x into our second equation to have y equals 3 times 1 minus 9. 3 times 1 is 3. 3 minus 9 equals -6. These are the coordinates of the center of our circle. Next is to compute for the radius of the circle. We can see from the figure that the radius is simply this stretch of distance from the center up to point B, which is 10 units. Therefore, r is equal to 10. From here on, we can now proceed with the usual solution for determining the standard equation of our circle.